Okay, so we're going to be presenting today on CTL19. I'm Ben, and my partners are Amy and Niche today. So, what's the first word that comes to mind when I say genetic engineering? Is someone
making new animals?
Making new animals.
Changing the genes.
Changing the genes. Okay. Anyone else? No, not you again. Okay. So, what we're going to talk about today is genetic engineering for cancer, specifically leukemia. So, our therapy is the genetic engineering of T cells to fight B-cell cancers.
So, there are a couple current treatments for acute lymphocytic leukemia, or ALL. The two most common are chemotherapy and radiation therapy. However, these therapies are non-specific. They target all cells, both healthy and cancerous. And the overall survival rate is only around 40%. Another therapy is stem cell therapy. It's fairly new and pretty expensive. This therapy really focuses on destroying or killing off the cells in that part of the body and then using a stem cell or like a master cell to recreate all the cells. I actually have a personal connection with leukemia and lymphoma. My great uncle, he was diagnosed with stage 4 lymphoma about a year and a half ago. I saw the effects on him really rapidly, and he died within 6 months of his diagnosis. Also, my uncle, he had leukemia about 14 years ago, and he went through both chemotherapy and radiation therapy. I was too young to remember this, but I've been told a lot that he suffered a great amount and he almost lost all his will to live. The only thing that kept him going was his 6-year-old son at the time. Okay, so how does CTL019 work? It targets CD19 positive cells. These are cells that express a protein called CD19. CTL019 is an immunotherapy, or a treatment that uses the patient's own immune system to fight the cancer. In the study that we researched, the doctors would remove healthy T cells, not all of them, from the patient and inject them with what is called a lentivirus that held 3 genes: the CAR gene, a chimeric antigen receptor, the CD137 domain, and the CD3 zeta domain. These T cells were then put back into the bloodstream. As they move through the bloodstream, they come in contact with B cells. The CAR receptor would direct the T cells to bind to the B cells, as shown here. Once the CAR receptor bound to this CD19 protein, the 2 domains, CD137 and CD3 zeta, would activate a series of signals that activated enzymes in the B cells, leading to B cell apoptosis. Does anybody know how to explain what exactly the CD137 and the CD3 zeta domain proteins did? Anybody?
Why don't you go over it again?
Yeah.
Okay. So basically, once the CAR receptor bound to this CD19 protein, the CD137 domain and the CD3 zeta domain would activate signal cascades inside the B cells, activating enzymes in the B cell that triggered apoptosis.
To clarify, the B cells are the cancerous cells.
Could you point on the diagram to what you're talking about rather than the words?
Okay. So the CAR receptor is here.
Okay.
The CAR receptor binds to this CD19 protein, and these 2 domains will be activated once it's bound. It sends signal cascades throughout the tumor cell.
Which one's the tumor cell?
The tumor cell on top.
Which is a B cell.
It's the B cell, and causes apoptosis eventually. Julia?
How does the apoptosis cause? What happens that causes apoptosis?
So,
You can take
specifically, so the activation of these 2 proteins activates enzymes inside the T cell itself, which activates what's called serine protease function. Serine protease function activates a signal, a cascade in the tumorous B cell, which causes apoptosis. Can we hold questions until the end? We need to stay on time. I'm sorry. Well, just write down your questions and we'll answer them at the end.
Okay, so here we have two graphs. I'm going to start with graph D. And so what they did is that they did these trials in mice. And here along the x-axis, you have the number of weeks, 0 through 5. And on the y-axis, you have the amount or the concentration of the cancerous B cells, which express the CD19 protein. So these two lines up top, here's the key, are the mock and no T cells. And these correlate with really high levels of the cancer cells. But when they introduced, which are these three, the T cells with the receptor, the amount of the cancerous cell was much lower. So what you want to get at graph D is that the modified T cells with the receptor lead to lower levels of cancer cells. Does anybody have any questions?
Is that because the B cells have activated apoptosis and they're killing off
Yeah, that'd be good. Okay, so I'm going to move to graph F now. So the x-axis and the y-axis are the same, the amount of the cancerous B cells and the weeks. The no T cells and the mock T cells, these two are correlate to high levels of the cancer cells. And then here's where it gets a little bit confusing, so stick with me. This line right here is the same as this, so it's just the T cell with the receptor. So that is over here. And then under it, these two are the T cells with one of the signaling domains. So this line has the CD137 domain, and this line is the CD3 domain. So both of those are lower than just the T cell with the receptor. And then here, the bottom line is the T cell with both of the signaling domains. So what's important about graph F is that the most effective combination was the T cell with both signaling domains, because that had the lowest amount of B cells.
Does anybody have any
Any
questions?
questions on the graph? And if you think of one later, we can come back to it too.
Wait, so did you say the signaling domains are the lowest amount?
Yeah, so they tested the T cell with one signaling domain, and they tested the T cell with the second signaling domain, but it was most effective when the T cell had both of the signaling domains in addition to the receptor. Nice.
Okay, so CTL19 therapy is actually not FDA approved as of right now. It's being produced by Novartis Oncology, and it currently just finished phase 2 trials actually in October of 2014. So phase 2 trials were conducted at the Children's Hospital in Philadelphia with 30 patients, some of whom were adults, some of whom were children. Now, 27 of the 30 were in complete remission after therapy within a few weeks of having therapy, which is a remarkable increase compared to the 40% survival rate. As of today, or at the end of the study, 19 remained in remission after having CTL19 therapy. 4 went off study due to complications in health, maybe other therapies or a complication in this cancer, and 7 relapsed. 3 developed CD19 negative cancer. So if you guys remember, this therapy targets CD19 positive ALL cells. So the leukemia actually mutated itself and then stopped expressing CD19. And if it stops expressing CD19, then the therapy can actually attack those cells. 3 relapse after an early loss of modified T cells, meaning that the T cells didn't take to the person, or they didn't proliferate in the person, or weren't able to complete their function. The overall survival rates of patients in the study were 78% for 6 months, which is a 38% increase over the almost 40% previously in leukemia. So that's almost double the survival rate. This chart over here shows you, if you look at the key, it says positive red plus means CD19 positive cells are above or equal to 3%. blue circling means CD19 positive cells are below 3%, and R means a relapse. And these are 30 patients, the amount of months. As you can see, there are a lot more blue circles than red pluses. Anywhere that there's a blue circle and blacks or red plus means that they haven't relapsed yet, and R means a relapse, and a plus is CD19 positive cells are still present. So, question?
Why is it that the blue keeps going like for 12 months? Why are there? It doesn't look like it's changing.
Because no. So this is the amount of time. These are each individual patients. So if it keeps being a blue dot is every time that they are tested for CD19 cells. So what you want is a long line of blue circles, meaning that they've been CD19 positive. The amount of CD19 positive cells is below 3% over an extended period of time.
But that means they still have it, right?
I mean, less than 3%, so it would be not as significant.
Do healthy people have CD19 in their body, and can you live with a small amount of it?
I'm not sure about that. That wasn't on here. We're going to move on to the next slide, which is side effects. CRS and encephalopathy. So, with any cancer treatment, there have to be side effects for something so invasive. So, in the 30 patients study, all 30 patients experienced cytokine release syndrome, which is due to higher levels of cytokines in the body. However, higher levels of cytokines in a person's bloodstream is directly correlated with T cell activation and proliferation. So in a way, having this is good because it tells you that the T cells are actually working in the body. 8 of the 30 patients had severe CRS, 22 had mild to moderate CRS, and symptoms of CRS include high temperatures, muscle aches, internal bleeding, coagulopathy, which is basically the inability for your body to clot, like bleeding. However, with the usage of an antibody, tocilizumab, all patients recovered from their symptoms. 13 of the patients also experienced encephalopathy, which is basically a disorder associated with your brain. So hallucinations, aphasia, or confusion are all examples of symptoms. Symptoms only lasted 2 to 3 days in the patients who experienced it, and all recovered without external aid or medication. So, in ways, it's not significant as cytokine release syndrome. Does anybody have any questions about the last 2 slides or anything that I can clarify?
Good question. Isn't internal bleeding kind of bleed to death sometimes?
Yes.
So how were they able to recover like that?
They recovered with the help of the drug. So tocilizumab is an immunosuppressor, so basically it shut down the immune response. So cytokine release syndrome is inflammatory response in your body due to higher levels of cytokines, and it causes all of those symptoms. By shutting down that immune function, basically they were able to prevent the symptoms from getting too far. Okay, we're going to move on and have questions at the end.
So why is CTL-019 important? It's the first personalized cellular treatment to receive FDA breakthrough status. So that means that it's the first, the FDA breakthrough status means that its pipeline process will get expedited and it'll get sped up. And so the trials show that CTL-019 is more effective in terms of overall survival rate than chemotherapy, because chemotherapy's overall survival rate is 40% and the CTL-019 is 78%. And then T-cell engineering can also be applied to other diseases. So you can take out somebody's T-cell or any cell and engineer it and then put it back in, and it could also be used to fight other diseases and illnesses, and that's a really important concept for the future. And we have a couple of acknowledgements, so special thanks to Mr. D and a couple of the doctors that helped us, and Arjun Patel, Alexa Buckley, and Andrew Verdesca.
And also the Kaplan family for letting us use their house as a place to use our resources. Thank you.
And now we can take any questions you have. We can go back to the presentation, anything that needs to be done.
I have a question. Can you go to the one where you say 7 people have relapsed? So you have 2 3s, but where's the 7th person?
Well, so we went through the journal itself. The journal actually wasn't very clear about what happened to each of the individual patients. We believe that the patient, the article made reference to a certain patient 11 who left the study very early on, as you can see, due to I think it was myelodysplastic syndrome.
What journal was it?
It was New England Journal of Medicine. But yeah, that one patient left, so we believe that he relapsed and he was the patient that's missing. But he could also have been one of the 4 who left the journal, left the trial, so he's one of those 2.
Can you go to the mechanism side?
This one or?
That. Okay, I don't understand specifically what, or even what CTL019 is.
Okay, so CTL019 is just the name for the engineered T cells. So those are the T cells that have this receptor and the signaling domains that were put in there by scientists.
CTL19 is specifically this receptor. It was originally called CAR019, but it changed the name.
That's what it's Can you describe a little more detail, like the process of taking out the cells and putting them back?
Okay, so basically what they do is they actually like take out parts of your blood stuff, take out like cells from your bloodstream, and what they do is they inject what's called a lentivirus. A lentivirus is basically just a type of virus cell, like there are flaviviruses, and a lentivirus is a type of cell, like one that's commonly known as HIV. HIV is a lentivirus, and what they do is they put in a gene to the specifically designed lentivirus, and those genes will be put inside a T cell, and through reverse transcriptase, I believe they become a part of the cell's genes. I don't know specifically what actually happens inside the cell once they inject it, because that wasn't part of it.
What pathway is that activated? Like what's happening inside the cell? What exactly? Like you said, when those 2 receptors bind, it activates domains.
Yeah.
Those are signaling pathways after that, right?
Yeah. They create signal cascades in the tumor cell, which will activate enzymes to cause apoptosis in the B cell.
Which is the tumor cell?
Do you get that?
So you said that this causes apoptosis in the tumor cells. So where exactly does this like interrupt a certain pathway in the cell cycle?
Like, can you specify what you mean by pathway, as in like what function of cancer does this interrupt?
I don't understand because like we learned different pathways that activate like transcription factors and stuff like that, and this specifically causes apoptosis. So I just don't understand like where this lies.
So in cancer, from what I understood from the class, is that cancer is able to shut down mechanisms that are within the cell that prevent that cause apoptosis. So it's able to take away those checkpoints. This is like an override where like an external cell comes in and tells it to prevent apoptosis.
So is CD19 receptor or attached to only tumor cells or healthy cells?
I'm not sure what that was specified.
Okay, I was going to say because I'm thinking about this, how this affects or modifies the T cells affects that.
Well, we know that, that in the mice that received no T cells, they had really high levels of the B cell. So that in the mice that did receive the T cells with the receptor, the levels got lower. So we know that the CAR receptor helps combat B cells cancer.
So, you said before had like a much better response rate, like 78%. So, why is it like not as widely used? Like, are there any only available to certain stages?
It's just very new.
Yeah, it's phase 2
Yes,
trial.
phase 2. So. And phase 2 was only finished last month. So.
Out of here,
CAR receptor will only bind to the CD19
So,
protein?
only tumor cells express the CD19.
Let me cross that. So all the B cells in the cancer, the CD19 positive cancer, express this protein.
So if regular cells express the protein, your treatment will attack the regular cells. The journal doesn't specify that.
Doesn't specify.
The CD19 in a healthy cell.
I believe it's an antigen, but other than that, the journal didn't really say.
Can you go to that phase 2 trial? Oh wait, no, sorry, it wasn't that one. It was the other one that I need to present. Yeah, that one. So, I'm sorry. No, just a minute.
It's okay. Does anybody else have any questions?
Wait, sorry. I don't know who was talking. I think it was Yelena, because I couldn't see it. Was asking how apoptosis was triggered. Right? Is that you? Okay. And you. The tumor cell, the T cell, is activating a pathway that somehow translates into the tumor cell. Is that what you're saying?
Yes. So if you look at your important terms sheet, T cells are like cells that they're kind of like B cells. They go around your bloodstream and will eliminate virus cells, pathogen cells, or even like malfunctioning cells. So basically, this is just a way for the T cells to identify tumor cells or bad cells in your bloodstream, and basically it activates what T cells would regularly do, which is attack those cells.
Okay, so the T cell binds to the tumor cell, specifically at CD19.
Yeah.
What is next in the exact mechanism?
That binding triggers for the 4-1BB stimulation.
In the T cell.
Yes.
Okay. Activating the cellular cascade in the T cell.
No, it activates the signal cascade in the B cell.
So
why are you pointing to the T cell right now?
no, so there's a cascade in the T cell of like, I don't remember the exact term. I think it was for enzymes or something. But those trigger serine protease, which triggers cascade.
Okay, serine protease in the T cell.
I believe so.
So we're now in the T cell. Does anybody understand my confusion?
Why is this pathway in the T cell instead of the tumor cell?
Right, so the serine protease is activated in the T cell, and then how do I get in the tumor cell? Now you're saying, okay, so just keep going. Serine protease is activated in the T cell, right?
And that triggers a cascade.
Where is that trigger?
Where does it on this particular illustration?
Yes.
It's not on that illustration.
How does a pathway, a protein that becomes activated inside of one cell, trigger something in another cell?
Signaling proteins through enzymes.
That's not depicted on the slide.
No, not this is portraying the binding of the CD19 to the CTL019 receptor. As shown by this figure. Gotcha.
So when they're bound together and the T cell transmits a signal into the tumor cell for apoptosis, does the T cell die with it? What happens to this T cell after the tumor cell dies?
It's not specified. No, it's not specified.
I remember my question now. Can you guys go to the graphs that you did? So in that second graph F, I was confused as to what these signaling domains were? It's like 2B, BB?
Okay. So
Are those other names for?
this one is the 137 signaling domain, CD137. And this one is the receptor plus the CD3 domain. And then this one is the receptor with both the CD3 and the CD137.
Okay.
And when it had both the receptor and both of the signaling domains, then it had the least amount of B cells. That's
Doesn't like that like in T cells or like does it do T cells also like cause cascade have B cells that aren't exist?
All the B cells express the CD19 protein, so it will
In
affect
ALL.
in ALL cancer. John.
You say they have the least amount of B cells, but in what? What do they have the least amount of B cells in? Like in the tumor?
This is concentration.
so
It's a
the
concentration of the B cell.
the B cells are the cancerous cells.
Yeah.
So that is just, so this line right here is the least amount of B cells, so the least amount of cancer cells.
So this would it's also
Yeah, what I'm asking is where?
it's in concentration in your bloodstream because leukemia is blood is basically
blood cancer,
a
yeah.
blood cancer. So if you look at the units, it says cells per milliliter and CD19 positive ALL cells per milliliter. So this would represent after 5 weeks, no T cells had no T cell therapy, there would be 400 ALL CD19 positive cells per milliliter.